Okay, students, I wanted to give you some examples of how to do some confidence interval problems and some hypothesis testing problems. We are going to be doing a lot of these in the upcoming remainder of the quarter. We're going to look at different situations and how to do them in different situations from here on out. So it's a good idea to kind of get some foundation down in there. And here is a bunch of sample problems, and I'm just going to work through them. I have my problems here, and then I also have a tab open into the ebook, into Table A, and a tab open to Table C as well, just so it's quick and easy to convert back and forth between those two. It's always a good idea to do that. You can log into Achieve multiple times. You can log into Canvas multiple times, and that can kind of help you get to these things all at once. All right. So question 1 says a soft drink machine is regulated so that the amount of drink dispensed is approximately normally distributed with a standard deviation equal to 1.5 liters. We want to find a 95% confidence interval for the mean of all drinks dispensed by this machine. If a random sample of 36 drinks had an average content of 2.25 deciliters. So our confidence interval formula is mu, the mean of our population, mean of all drinks, is going to be, our best guess is x bar plus or minus z star sigma over the square root of n. And so our best guess for the average content is going to be our sample mean, 2.25. And then I want to do plus or minus a z star. So I want the critical z value for 95%. That is saying kind of on that normal distribution, how far out do you have to go to capture 95% of your values? And we know it's approximately 2, but I'd prefer you to be a little bit more accurate using the value here in Table C. In Table C, we've got a confidence level across the top, and there's the 95%. And I want to go all the way down to the bottom of that table, keeping track of that sort of that middle column there until I get to the end. And I got some of those highlighted for some reason, but it's right here, 1.960. That was in the 95% column, is the Z star down at the very bottom of that table C. So I know Z star is 1.960. And standard deviation of our population was 1.5. I'm going to divide that by the square root of the sample size in there. And that should give us our confidence interval. So let's pop over to the calculator and do the math. I'm going to do just the margin of error first. 1.96 times 1.5 divided by the square root of 36, calculating the part after the plus minus, the margin of error section of that, and that's given me 0.49. So my margin of error, my confidence level would be 2.25 plus or minus 0.49. And we can leave it like that, or we can actually do the math if you want. Either way, you'll see confidence intervals reported both directions, both ways, so you want to kind of be familiar with that. If you do the subtraction, we get 1.76, and 2.25 plus 0.49 is 2.74. Okay, 1.76 and 2.74. All right. And so we could say something like we are 95% confident that the mean amount of drink dispensed is, and then you kind of have two alternative endings here. You could either say is the 2.25 plus or minus 0.49 deciliters, or we could say is between 1.76 and 2.74 deciliters. And either one of those is an acceptable sort of response. You'll see them in different publications listed sort of different ways. So you want to get used to seeing them both as the plus or minus or between this value and that value in there. So it's kind of two different options on how you can choose to end that out. All right. We have random height of 50 college students, showed a mean of 174.5 centimeters and a standard deviation of 6.9 centimeters. What can we assert with 95% confidence about the possible size of our error if we estimate the mean height of all college students to be 174.5 centimeters? So that's really looking at the margin of error here. We're going to say that our mean is still x bar plus or minus z star sigma over the square root of n. And so 174.5 would be our mean, and the margin of error, the size of our error, we are off by here. We're looking at 98% confidence. So I want to go to table C again and find 98% confidence, and it's way at the top and the confidence levels are at the bottom. So we're going to fix this column. Keep track of what column that is, where the 98% column is. It's got the 31 in it there at the top. I'm going to follow that same column all the way down here, all the way down to the bottom, and it is 2.326. 2.326 was the z-score corresponding to that. So 2.326, 2.326. Plus or minus the standard deviation of a population, 6.9 over the square root of the sample size. And we looked at 50 college students in there. And I'm just realizing that this question is actually from a previous, a later section that we have to go over yet still. Let's just assume this is the population standard deviation. If we read this closely, we'll actually find it's the standard deviation of the sample. And that means we have to do something other than a z-test, but we're not there yet. So we'll just pretend that is sigma. It's actually s, but we're going to pretend it's sigma for this problem because we're not quite there yet. In chapter 20, 1920, we're going to talk about how to deal with when you don't know the population standard deviation. All right, but we're really looking for that error. So 2.3, I forgot the number. 2.326, 2.326 times 6.9 divided by the square root of 50. All right, and so that's giving me a 2.27. We'll call it 2.27 for our standard deviation there. So 174.5 plus or minus 2. I said it so many times, but I still can't remember. 2.27. 2.27 centimeters. So we're off by, we're 98% confident that we're going to be within 2.27 centimeters of the true mean. Well, if you go 2.27 centimeters on either side of the true mean, you'll capture 98% of the sample mean. So our margin of error there would be 2.27. All right. And number 3 asks, how large of a sample do we need in question 1 if we want to be 95% confident that our sample mean will be within 0.03 deciliters of the true mean? And so what's that meaning is that we want to take that z star sigma over the square root of n, and we want that to work out to be 0.03. So we're trying to see how does that sample size influence that value there. 95% confidence, so we get to use the same z star of 1.960 times the standard deviation from question 1 was 1.5 over the square root of n. We want that to work out to be 0.3, so plus or minus 0.3, where you had a plus or minus 0.5 before, I want it to be plus or minus 0.3. All right, and so if I want to solve for n, what I can do is multiply both sides by the square root of n. .3 times the square root of n. Then I'm going to divide both sides by 0.3. So 1.96 times 1.5 divided by that's a 5 there. Divided by 0.3 would equal the square root of n. And then finally I'm going to square things to get rid of the square root. So n would equal 1.96 times 1.5 divided by 0.3, that whole thing squared. And so let's go over to the calculator and do that. So I'm going to take 1.960 times 1.5 divided by 0.3, and I want to square that whole answer, and I get 96.62. You can't interview 0.62 of a person, and so I need 97 drinks is what I need in my sample. Okay, and you always want to round up your sample size, even if the normal rules for rounding say round down, always round up, because that will guarantee, that will make your margin of error a little bit smaller than what we're shooting for there. You have to round to a whole number, because you can't do half of a test. It's either, you're either doing 97 drinks or 96 drinks. You can't do 96 and a half drinks. But always round up. Always round up your sample size. A simple random sample of 1,000 recorded deaths in the past year showed an average lifespan of 7.8. And we're going to assume the standard deviation is 8.9 years. Find a 95% confidence interval for the actual lifespan. So another confidence interval, mu is equal to x bar plus or minus z star sigma over the square root of n. So mu is equal to our sample mean, 71.8, plus or minus z star. Again, I'm going to go back to my table, and I'm looking for that 95%. So 95% is in this column. Maybe put a finger on it in your screen as I scroll down so you can follow it all the way down here to the bottom. We've looked it up a couple of times already, but doesn't hurt to look it up again. Z star all the way down here, 1.960 as our Z star. So 1.960. Standard deviation was 8.9, and our sample size was 1,000. Okay, and so let's crunch those numbers. 1.96 times 8.9 divided by the square root of 1,000 gives us 0.55. So we're looking at 71.8 plus or minus 0.55 years. So we are 95% confident that the mean lifespan is, let's just say it that way, 71.8 plus or minus 0.55 years. You can also, of course, do the plus, the minus thing, and say it's between, what you get with the subtraction and what you get with the addition like we did up here, we could say it's between, year 1 and year 2, whatever those worked out to be. Or you can do it as just the plus minus in there. Okay, so we have a certain national test, school test with the mean of 500 and a standard deviation of 1,000, or standard deviation of 100, and a principal claims that her students are above average. She takes a random sample of 75 and finds the mean of those 75 students is 525. Is her claim justified? Well, supposing that what we're looking at here, this is a hypothesis test. We want to test a set of hypotheses to say, is the mean of her students above the national average? So we might start with a null hypothesis, is that mean is equal to 500, and an alternative hypothesis is that the mean is greater than 500. So the null hypothesis is saying that students at this particular school are the same as the national average. There's no difference in there. And our alternative hypothesis is what the principal hopes to be true, is that the mean is more than 500 in there. And that's kind of the first step of doing a hypothesis test. You want to state your hypotheses. And then we want to find our test statistic. So I'm going to calculate a z-score. X bar minus mu divided by sigma over the square root of n is going to how we're going to find that z-score in this particular case. As we go on, we're going to talk about different ways of carrying out hypothesis tests. It's going to have these same 4 steps. The difference might be in how we calculate our test statistic and how we find the p-value. But same sort of steps we'll go through there. So I'm going to take my sample mean, which was 525. The population mean is 500. The standard deviation we're looking at is 100. And my sample size was 75. So that's going to calculate my z-score for me. Let's go to the calculator and do that. It was 525 minus 500 divided by, and then you do have to put this in parentheses, your standard deviation over the square root of your sample size. That's got to be in a set of parentheses. That bottom calculation needs to be in a set of parentheses on its own if you're going to do that all at once. All right, and we come up with 2.17. We'll call it 2.17. The textbook rounds our z-scores to 2 decimal places, so we'll do the same here. So 2.17. All right. Next, I want to find the p-value. And so I'm going to go to Table A to do that. It's a z-score, and our z-scores are in Table A. So Table A, I'm looking for a z-score of 2.17. So 2.1, I want to go to the 2.1 row. Whoops. 2.1 row, and then I want the 7 column. So this is 2.10, 2.11, 2.12, 2.13, 2.14, 2.15, 2.16, 2.17. Maybe it was easier to go the other way, but that's okay. I get 0.9850 as my p-value. And so that is not quite the p-value that I'm looking for here. My p-value is going to be 1 minus 0.9850. I'm subtracting for 1 in this case because I'm doing an upper tail probability. I've got a greater alternative hypothesis that's more than 500. And what I'm doing when I'm finding that p-value, the central limit theorem says that my sampling distribution, that if I looked at lots and lots of different random samples and the mean was really 500, I'd see a normal distribution with a mean of 500 and a standard deviation of 1,000 divided by the square root of 75. And what we're trying to do is we're trying to find the probability that I end up with 525 or more. What's the chances that I end up with a sample mean of 525 or more if the mean is really 500? And that's going to give us our p-value here. And so you're looking at this upper tail probability. The table, the textbook table, Table A always gives you, if you look at the picture, it's always giving you the area to the left. I want the area to the right. The total area is 1. So if I subtract from 1, I'll get that upper tail probability in there of, let's see, 0.0150 would be what that is. Okay, so there's a 1.5% chance of getting a sample with a mean of 525 if the mean is really 500. All right, and so then we have to make a decision to say whether or not her claim is justified. That's a, what do you think? I mean, to me, that's a very small probability. It's very unlikely that I should get this sample of 525 if the mean was really 500. So I'm going to do my conclusion. I'm going to reject the null hypothesis and say that the sample suggests the mean of students at the school, of all students at the school, is above 500, is above the 500, the national average there, in there. So we would not, it's unlikely we should not see this random sample. It's very unlikely we get a random sample with a mean of 525 if the mean is really 500, and because that's a small chance, I'm going to reject the null hypothesis. Okay. And so that's one of the things there. It's a little bit of a judgment call on, do you think that p-value is small? If you think the p-value is small, you reject the null hypothesis. And if you feel that it's not, if it's a large chance, if it's likely just that sampling variation, then you'd fail to reject the null hypothesis in there. So that's kind of what we're looking at there. Okay, so 4 steps to that: state your hypotheses, find the test statistic, find the p-value, and write a conclusion. And I look for all of those when you do your homework, when you do your some of the multiple choice questions in the homework are they lead you through all those steps. If you look at it, they're actually taking you through those steps, but I want to see that on tests and quizzes, that you show all 4 of those steps to get full credit on there. All right, so here's another one. A random sample of 100 recorded deaths in the United States during the past year showed us an average lifespan of 71.8 years. Assuming the standard deviation of 8.9 years for the population, can we conclude that the actual lifespan is not 75? Okay. And then this one gives us a significance level of 5% value. So that's what's defining, the significance level is defining what's small there. So up here on the one before, we had to make a judgment call as to whether or not 1.5% was a small percentage chance. Here with a significance level of 5%, that's kind of defining small. What we'd want is a percentage less than 5%. If our p-value is less than 5%, then we're going to reject the null hypothesis. We want an observed value so far away from the mean that it has less than a 5% chance of happening in there. So that's kind of nice to have that there. All right. So same 4 steps. I need to start with my hypotheses. Mu equals, the null hypothesis is always a mu equals some number. And you want to look at, there's kind of 2 averages in there. You've got this average here of 7.8, but that's from the random sample. That's your x bar, is the 71.8. And so the other number, the other mean that you have is going to be your population standard deviation, or your mu. It's going to be the mu that you're talking about. So our null hypothesis would be the mean is 75. And then the alternative hypothesis, this is an example of a two-tailed one, because we're just saying that it's not 75 for our alternative hypothesis. In there's no claim of it's greater than 75 or less than 75. So it's a two-tailed with that not in there. All right, so two-tailed. I'm going to calculate my z-score. That's going to affect how we calculate the p-value here in a little bit. We're going to calculate my z-score using the same kind of idea. I want to look at in terms of standard deviations. How far is the 71.8 from the 75? Sigma over the square root of n. So I'm looking here at 71.8 minus 75 divided by 8.9 over the square root of 100. And that's going to calculate out my z-score here. 71.8 minus 75. So in parentheses, 71.8 minus 75, close parentheses, divide by, and then in parentheses you want the 8.9, your sigma, divided by the square root of your sample size, square root of 100. Be sure that you are getting that in there with parentheses around the top and around the bottom. So that those calculations happen before the big division in the middle. And negative 3.59, negative 3.59, actually negative 3.60 if we round to the closest value. All right, so negative 3.60. Okay, and then I'm going to look for the p-value. Again, this is a two-sided one. What I came up with was the mean was 75. We're going to assume the null hypothesis is true. So our standard deviation, our sampling distribution, has a mean of 75. So what I want to look at is what's the probability that I get something less than 71.5 or greater than that same distance on the top side. So 71.5 is what, 3.5, or 71.8, sorry. 71.8. 71.8 is 3.2 units below. And so I also want to look at 3.2 units above 78.2 it would be. So I'm looking for the area that's below 71.8 or above 78.2. But the nice thing about the normal distribution is it's nice and symmetric, that if I find the area in one tail, all I have to do is double it to get the area in both tails, because it's going to be exactly the same. Okay, so I'm going to take that negative 3.60. I'm going to go to the ebook to table A to look at that normal distribution, 3.60, and I am off the chart. Negative 3.49 is the smallest value I have. But let's go ahead and guess. We can take an educated guess that lower table, all of these leading up to that negative 3.40, 3.41, 3.42 are 0.0003, and then it changes to 0.0002. And so it's probably going to be 0.0002 for a while. We can probably guess that our p-value here is going to be 0.0002. But I do have to multiply it by 2 because of the two-tail thing. But I've got a very small p-value, much smaller than my significance level of alpha up here, up there. And so because my p-value is smaller than alpha, I'm going to reject the null hypothesis. If the mean is really 75, I really should not get a sample of 71.8. It's very unusual to get that sample, and so since I shouldn't be seeing 71.8 if the mean is really 75, I'm going to reject the null hypothesis. I shouldn't be getting 71.5 but I got 71.8. I shouldn't be getting 71.8, but I got 71.8. So I'm going to reject HO and then say our sample. I could even say, well, how about suggests that the mean, let me just adjust here a little bit. That the average lifespan is not 75 years at the, I could even add this in, at the 5% significance level. Okay, so using that 0.05 up there, I can come in and say that as well. All right. How about manufacturer of a sports equipment has developed a new synthetic fishing line that he claimed has a mean breaking strength of 8. We're going to test that hypothesis. So we're doing a hypothesis test with a 1% level of significance. So first step is to state your hypotheses. Our sort of assumed mean would be 0.8 kilometers or kilograms. And then the alternative hypothesis would be we're concerned that it's less than, we want to test the alternative that it's less than 8 kilograms. Those two should be the same number every time. On your null hypothesis and your alternative hypothesis, you're going to use the same number on those in there. We did a random sample of 50 and found a mean breaking strength of 78. And again, we're going to assume sigma is equal to 0.8 kilograms. We're not measuring it. We're going to not measure it from a random sample. We're going to assume that it's 0.8. We're going to assume that in there. And we're going to use a 1% test of significance. So we've got our hypotheses. That was the first step. The next one is to calculate your test statistic, your z-score. I'm going to take x bar, our sample mean of 7.8, minus the population mean of 8, and then divide by your standard deviation over the square root of your sample size. We did 50 lines there. 0.8 was our standard deviation of our population. So that's that. Let's flip over to our calculator. It was 7.8 minus 8 divide by the standard deviation, 0.8, whoops, got to be in parentheses, 0.8 over the square root of 50. Yeah, that's probably okay. All right, so I got a z-score of negative 1.77. Negative 1.77 for my z-score. So let's go back to this, negative 1.77. So z-score, and then I need the p-value. It's a less than sort of alternative hypothesis. So I'm kind of anticipating that my sample mean would end up over here. I'm looking for this tail down here. I'm looking for the probability that I can get a mean of 7.8 or less if the mean is really 8. And so I want to look at the p-value. I can take the number straight out of table A, negative 1.77. Negative 1.7. Way over here is 1.79. 78. So I'm looking at 0.0384. 0.0384 is my p-value. Are we seeing that okay? I hope you're seeing that okay. 0.0384 with a negative 1.77 in there. Should be there, 0.0384. So my p-value is 0.0384. That's what I said, right? Yeah, 0.0384 as my p-value. And what I note here is that that's greater than my alpha. And so there's a 3% chance that I can come up, or 3.8% chance I can come up with a 7.8, a sample with a mean of 7.8 or smaller. But I want something far enough away that there's less than a 1% chance of getting it. And so this is too big of a percentage. Even though it's small, I'm going to, based on the significance level, fail to reject HO. We fail to reject the null hypothesis. And then we could say something that although the sample mean was less than 8 kilograms, the difference was not significant. At the 1% level, or the 0.01 level in there. So we got a difference, but it's not statistically significant. All right, do I got one more to do? I got 2 more to do here. Okay. Trucking firm doesn't believe that the claim that the average lifespan of certain tires is at least 20,000 miles. To check the claim, the firm puts 40 of these tires on its trucks to get a mean lifespan of this value. We're going to assume a standard deviation. Sigma is equal to 134.8 miles in there. And we want to do that with a significance level of 0.01 out there. So another hypothesis test here. Our null hypothesis would be that the mean is equal to 27,000. And then our alternative hypothesis, the trucking company is concerned that it lasts less than the 27,000. If the tires wear out too early, they might think they're being overcharged for the tires in there. So from the trucking firm standpoint, those are the null and alternative hypotheses. I want to calculate my z statistic. So this is a less than sort of thing again. So I'm anticipating looking at this lower tail sort of probability when I'm trying to find my answer here. So I'm going to take x bar 27563 minus 27,000, sorry, divided by 134.8 over the square root of 40. 134.8 over the square root of 40. All right, so let's jump over to the calculator. 27, of course, then you have to remember the numbers. 27,563. 27,563 minus 27,000 divided by 134.8 divided by the square root of 40. Whoops, not 409, 40 in there. I think those are the right numbers. Let me try the minimizing thing. Oops, that didn't work the way I wanted it to. Yeah, 134.8 over the square root of 40. All right, back to the calculator and enter, and 26.41. Wow, that's huge. 26.41. Okay, so that's my z-score. 26.41. That is way off the charts. And that's way off the chart. If I look at 26, it only goes up to, oops, gone too far. It only goes up to 3.49 on our chart here, 3.4, and then the last number over here is 3.49. And so I'm quite a bit larger than that. So I'm going to say that the p-value is essentially 1 in there. So in that case, we're obviously going to fail to reject the null hypothesis. Failed to reject the null hypothesis and says that the maybe the sample does not suggest the mean is less than 27,000 miles at a significance level of 0.01. There, that's a good statement there. Good way to write that out. You can kind of tell this one went sort of the wrong way. Our sample mean turned out to be larger than the hypothesized mean of 27,000. So we ended up on the wrong side in there. So this one's kind of weird in that way that we ended up on the wrong side. All right. And then finally, we've got a fire insurance company that felt the mean distance from a home to the nearest fire was at least 4.7 miles and set its rates accordingly. Members of the community sent out the mean distance was less than 4.7. And so they want to try to lower their rates because they're closer to the fire station, meaning the fire company can get there faster, put out the damage so there won't fire faster, so there won't be as much damage in there. But our null hypothesis would be mean at mu is equal to 4.7. The community is hoping to show that the mean is less than 4.7, that they're closer. And so we randomly chose 64 homes, measured the distance to the nearest fire department, and found that the sample mean was 4.4. We've got a population standard deviation of 2.4. And so let's go ahead and calculate our z-score. I'm going to take my x bar, the 4.7, or 4.4, subtract our population mean of 4.7, divide by sigma 2.4 over the square root of 64 to get my z-score there. All right. And so 4.4 minus 4.7 on top. Divided by, on the bottom was 2.4 over the square root of 64. That's a nice number, but we could do that in our heads, but that's okay. So -1 is what I'm coming up with as my z-score. So -1. And then I want to find the p-value. Again, this is a less than alternative hypothesis, so I'm looking for that lower tail probability, and it should be just the number straight out of the table. So a -1 in table A gives us a p-value, there it is, 15.87.1587. That's the very first column there, is the 1.00 is 15.87. So 0.1587. There's a 15% chance that we can get a sample with a mean of 4.4 or smaller if the mean is really 4.7. And so that's certainly greater than the 0.05. So when that happens, we fail to reject the null hypothesis. And then we can say something that although the sample mean was less than 4.7 miles. The difference wasn't statistically significant at the 0.05 level. At the 0.05 level, so we're at the 5% level. So it's likely, I mean, we get variation when you take a random sample from the population. You don't always get the exact same sample mean as the population. There's some variation from sample to sample, and this is within our sampling variability. The chances are that we can get that difference. It's pretty good. It's a pretty good chance that we can get that just by random chance. So we'd have to say we failed to reject the null hypothesis. All right, and that's all of them. I hope you enjoyed this.
I found the vouchers.